Hello everyone. This is one of the system wiring diagrams in the EG4 18kPV hybrid inverter installation manual. It happens to be the one I'm using, but with two minor differences in the AC circuitry. You're welcome to pause the video for a longer look at this. But this video is focusing exclusively on the interconnections in this part of the diagram, and how I selected the appropriate size AC conductors for the 240 volt AC 100 amp circuit shown here. Here's the all-in-one inverter. This is a disconnect to be mounted on the outside wall of the house, close to the electric meter. And here's the main service panel. This light gray upside down T represents a PVC conduit that houses the 240 volt AC 100 amp circuit conductors as shown. There's up to 100 amps of 240 volt AC passing between the grid terminals in the inverter and the inverter circuit breaker in the main service panel in the black, red, and white conductors as shown. The task at hand is to determine the proper size and type of conductors to use for this circuit. Before we move forward, pause the video and write in the comments, what size conductors would you use? Just so you know, this circuit might be feeding power from the grid to the inverter to charge the batteries. Or it might be using the inverter's pass-through feature, which passes grid power through the inverter to the loads in the event the loads exceed the inverter's power capacity. In other words, if the inverter can't meet the total demand of the loads from solar or battery power, it will take power from the grid to meet the additional demand, up to 200 amps. However, this is also the grid tie circuit, so when the inverter has any unused power, it can export that extra energy through this circuit to the grid. So for example, if there's 25 amps coming in from the PV modules and the house is using 15 amps, the inverter can export the extra 10 amps out to the grid and make the meter run backwards. But we need to have a net metering contract in place with the utility company before we can legally do that. The worst case scenario is when there's no solar power coming in and the batteries are dead. In this case, all the power going out to the loads is coming through the inverter, which is passing it through from the grid. And at the same time, the inverter charger might be charging the batteries as well, depending on how the firmware is configured. So this circuit would be carrying the charger current and the house loads as well. And what if the house load is 70 amps? How can these conductors carry enough current to charge the batteries? That's why I've chosen to provide a 100 amp circuit here, instead of the 70 amps in their diagram. Now moving ahead, there are 3 current carrying conductors in this section of conduit. There are also 3 current carrying conductors in this section of conduit. But there are 4 current carrying conductors in this section of conduit. And this section is probably going to be over 10 feet long. Let's look at the National Electrical Code. If you're currently learning the code, you might want to crack open your NEC book and follow along. If you don't have a book, check out my previous video about free online access to the NEC. Article 310.15 covers the ampacity tables. Starting at the top, A. General. Ampacities for conductors rated 0 to 2000 volts shall be specified in the ampacity table 310.16 through table 310.21. as modified by 310.15a through F and 310.12. I'll skip over the part about engineering supervision because it doesn't apply here. Next, the temperature correction and adjustment factors shall be permitted to be applied to the ampacity for the temperature rating of the conductor if the corrected and adjusted ampacity does not exceed the ampacity for the temperature rating of the termination in accordance with 110.14c. Let's see how 110.14c requires us to coordinate the conductor and terminal temperature limitations. First part, temperature limitations. The temperature rating associated with the ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature rating of any connected termination, conductor, or device. So the conductor has a temperature rating and the terminations on devices we're wiring have temperature ratings. And when we connect them, we need to respect the weakest links in the chain. For example, a conductor that's rated 55 amps at 90 degrees C can't be applied at 55 amps when it's connected to a 75 degrees C terminal. The conductor will have to be derated to its ampacity listed under the 75 degree column in the ampacity tables. Most circuit breakers have 75 degree terminations. The terminations on this Siemens circuit breaker are labeled in tiny fine print, but with a magnifying glass we see the terminations are rated for use with aluminum or copper conductors with ampacities in their 60 degree or 75 degree column. You can use 90 degree rated conductors here, but only at their 60 degree or 75 degree ampacities. Next part. Conductors with temperature ratings higher than specified for terminations shall be permitted to be used for ampacity adjustment, correction, or both. So when we're doing ampacity corrections on these conductors, we can apply our derating factors to its higher temperature rating to derive its derated ampacity value. But we still can't exceed the temperature rating of the termination. Keep that in mind. 110.14c1 Equipment Provisions. The determination of termination provisions of equipment shall be based on 110.14c1a or c1b. Unless the equipment is listed and marked otherwise, conductor ampacities used in determining equipment termination provisions shall be based on Table 310.16 as appropriately modified by 310.12. Now, 310.12 refers to dwelling services and feeders, and while there might be an argument for calling this circuit a feeder, I'm not comfortable using the less rigorous requirements of 310.12 for this circuit, especially considering the feeder ampacity ratings allowed by Table 310.12a. What do you think? Is 310.12 applicable to this circuit? It permits number 4 copper at 100 amps. I'm rattling through a lot of code here, but don't worry, it all applies to the example circuit, so it'll become more clear as we move through it. Let's see what 110.14c1a and b are all about. 110.14c1a, termination provisions of equipment for circuits rated 100 amperes or less, or marked for 14 AWG through 1 AWG conductors, shall be used only for one of the following. Notice that A applies to circuits of 100 amps or less, with a maximum conductor size of 1 AWG. Now take a moment to note that B applies to circuits over 100 amps, with a minimum conductor size of over 1 AWG. Since we have a 100 amp circuit, we'll only be reviewing A. So 1. Conductors rated 60 degrees. There are conductors in the tables that are rated for only 60 degrees. This column also applies to non-metallic cables like Romex. 2. Conductors with higher temperature ratings, provided the ampacity of such conductors is determined based on the 60 degree ampacity of the conductor size used. 3. Conductors with higher temperature ratings if the equipment is listed and identified for use with such conductors. Like this. Note, all of your circuit termination devices have to be 75 degree rated to apply this provision. 4. For motors marked with design B, C, or D, conductors having an insulation rating of 75 degrees C or higher shall be permitted to be used, provided the ampacity of such conductors does not exceed the 75 degree ampacity. So if we're wiring a B, C, or D motor, 100 amp or less circuit, we can use 75 degree or higher rated conductors, as long as we use the 75 degree column ampacity. 1, 2, and 4 don't apply to the circuit we're working, but 3 does. For our example circuit, we can use conductor ampacities with a higher than 60 degree rating, because the equipment we're wiring is identified for use in the 75 degree column. But wait, there's more. 110.14c2, separate connector provisions. Separately installed pressure connectors shall be used with conductors at the ampacities not exceeding the ampacity at the listed and identified temperature rating of the connector. So temperature ratings really apply to every device we use to make a conductor connection. The informational note indicates that markings or listing information may additionally restrict the sizing and temperature ratings of conductor connectors. Now let's get back to 310.15. Okay, we jumped from this statement on termination temperature settings to 110.14c. There's some informational notes just below that you can review on your own. Those will just bog this video down. Next, 310.15b1 General. Ampacities for ambient temperatures other than those shown in the ampacity tables shall be corrected in accordance with 310.15b11 or table 310.15b12, or shall be permitted to be calculated using equation 310.15b1. Let's start by selecting a copper conductor with an ampacity of at least 100 amps. So it looks like maybe a number 3 copper conductor will meet the need. But these ampacities are based on an ambient temperature of 86 degrees Fahrenheit. Now let's look at the possibility of correcting that ampacity due to an ambient temperature of greater than 86 degrees Fahrenheit. So we're starting this process by applying temperature corrections to our conductor ampacity table values. Here's where we start to see why all that code review was worth it. For example, if we're wiring a circuit breaker with 75 degree terminations, we can apply the 90 degree column for conductors with a 90 degree rating. A conductor's temperature rating is required to be marked by the manufacturer. Our example conductors will be in the cellar where the ambient temperature is less than 86 degrees or less, and on the outside of the house where the ambient temperature can possibly go as high as 95 degrees Fahrenheit in the summer. So I'd be wise to apply a correction factor of 0.96 to the conductor's ampacity of 115 amps. 115 amps times 0.96 equals 110 amps. So we're good. Number 3 copper will meet the need, right? It's not that easy. Because 310.15c1 requires additional adjustment factors if there's more than 3 current carrying conductors in the conduit. 310.15c1. Adjustment factors. More than 3 current carrying conductors. The ampacity of each conductor shall be reduced as shown in table 310.15c1, where the number of current carrying conductors in a raceway or cable exceeds 3, or where single conductors or multi-conductor cables not installed in raceways are installed without maintaining spacing for a continuous length longer than 24 inches. Each current carrying conductor of a paralleled set of conductors shall be counted as a current carrying conductor. Another interesting detail is that adjustment factors shall not apply to conductors in raceways having a length not exceeding 24 inches. So if the conduit is 24 inches or less, we don't bother adjusting the ampacity of 3 or more current carrying conductors. So how do we handle neutrals and ground conductors? It's pretty simple in this case. 310.15e1 says a neutral conductor that carries only the unbalanced current from other conductors of the same circuit shall not be required to be counted when applying the provisions of 310.15c1. The unbalanced current in a 120-240 volt system is the current that travels the neutral. That happens when there's more current flow on one of the hot lines than the other. If we had a perfectly balanced system, the neutral would carry 0 current because all of the current on the opposing 120 volt lines would create a 240 volt circuit. The diagram shows a 120-240 volt transformer with a black line 1, a red line 2, and a white neutral. Line 1 to line 2 is 240 volts AC. Line 1 to neutral is 120 volts AC, and line 2 to neutral is 120 volts AC. If we put a 120 volt 1200 watt load on line 1 to neutral, with line 2 being open, the neutral will have 10 amps flowing through it. If we put a 120 volt 600 watt load on line 2 to neutral, with line 1 being open, the neutral will have 5 amps flowing through it. If we put both loads on at the same time, we get current flow on both lines to neutral. But where does all that current actually flow? Does the neutral see 15 amps as it appears to here? What's really happening? The unequal current on line 1 and line 2 are called an imbalance. What's really happening is that the two 120 volt loads create a 240 volt load with 5 amps flowing between line 1 and line 2. The remaining 5 amps of unbalanced current on line 1 flows on the neutral at 120 volts AC. Considering that the heating effect of current flow on line 2 and the neutral combined is equal to the heating effect on line 1, the code doesn't consider it necessary to consider the neutral as part of the number of current-carrying conductors for derating purposes. Basically, I interpret it as those two equal one conductor, so only count them as one. So, the grounding and bonding conductors. 310.15f, grounding and bonding conductor. A grounding or bonding conductor shall not be counted when applying the provisions of 310.15c1. These don't count because they aren't current-carrying conductors. We finally arrived at the meat and potatoes of 310.15, table 310.15c1, adjustment factors for more than 3 current-carrying conductors. Recall that I have 4 current-carrying conductors in this conduit. Based on the number of conductors, I'll need to apply an 80% limit on the temperature-corrected ampacity of these circuit conductors. 88 amps isn't 100 amps, so we now know that number 3 copper conductors aren't going to work in this circuit. We need to go back to the ampacity tables and select a different conductor size. The next size larger is number 2 AWG. And we can start our derating adjustments with 130 amps. Let's run the numbers. 130 amps times the 0.96 temperature adjustment equals 124.8 amps. 124.8 amps times the 80% derating for more than 3 current-carrying conductors equals 99.84 amps. Okay, I have to admit, this is a conundrum. 99.84 amps is less than 100 amps. Technically, according to the letter of the code, I should increase the conductor size to 1 AWG. But I'm rationalizing that 99.84 amps is only 0.16 amp less than 100 amps. It's 160 milliamps. And a difference of 160 milliamps is virtually no difference on a 100 amp circuit. It's 1.5 tenths of an amp. 310.12 says a number 4 AWG copper conductor is okay on a 100 amp 3-wire dwelling service or feeder. Number 4 is only 95 amps capacity. The reason 310.12 says a number 4 AWG copper conductor is okay for a 100 amp dwelling feeder is that demand factors are already pre-estimated for a single unit dwelling. Number 4 is okay for 100 amps, for the same reason number 2 is okay for 125 amps. That number 2 feeder will never actually see 125 amps. In fact, in a course I took at a utility company, the engineer teaching the class said the average 200 amp service is running at less than 60 amps 90% of the time. So there's a lot of overhead built into these provisions. I know from experience with my house loads that this number 2 copper will never see anything close to 100 amps. If I'm charging my batteries at 30 to 40 amps and my domestic loads will not normally be pulling more than 40 amps for sure, my number 2 conductors will remain cool enough to be safe. So I'm confident that that 160 milliamp shortfall won't make any difference at all. So I'm going with number 2 copper on this feeder, and I'm sure there will never be a problem with that. But I have to say, unless you're an experienced technician, don't do as I do. Do as I say. In a case like this, if there's any doubt in your mind, select the next size up. This circuit could easily be a number 1 AWG to stay on the safe side, as less experienced people should always do. If there's something about this conductor selection process you'd like to talk more about, the comments are open for discussion. Please let us all know. Thank you for watching. Please take a moment to like and subscribe.